Hello everyone, welcome back to ThinkLab by Saurabh. So in today's tutorial we are going to build one of the most important architecture in modern natural language processing, the transformer, right? So we are not just going to use a pre-built transformer model. Instead of we are going to understand that what's happening inside the architecture and implement the important component, using the Python and TensorFlow. So our practical project will be sentiment classification of IMDb Movie Review dataset, and given a movie review our model will predict whether the review is positive or negative. So during this project we will understand the tokens, embedding, positional information, self attention, multi-head attention, and residual connection and layer normalizations, feed forward network and transformer encoder, as well as we can finally check the final classifications, right? So let's open the Google Colab and start building our transformer from the scratch, right? So you can see here this is the pipeline. You can on the screen you can see this is the pipeline. So we will follow this pipeline in throughout this project, right? So first we will use the IMDb movie review dataset, then we use the integration token sequence, then we perform the padding, token embedding, positional embedding, transformer encoder, multi-headed attention, adds norm, feed forward network, right? And finally we have used the global average pooling in dense layer and the sigmoid, and finally we can perform our, that's the final report, like it's a positive or negative, right? So let's start with the, first thing we have to just import the essential library. So I'm going to write here in the form of text, right? So in the we have to perform everything, we will perform everything in the Google Colab, right? So now we are going to import the all the importance library here. So I'm writing the importing the libraries, right? So first thing here we will import here, numpy, because we will to work with the numerical array. Then we import the TensorFlow, which will be used to build and train our neural network, right? And after that we will import the matplotlib, right? So matplotlib, later we can visualize our training and validation performance. Then we will use the Keras. So we will import the layer and model using this Keras. So I'm going to write here the all the important libraries, right? After that, Keras, after that important thing is to understand that although we are using the TensorFlow and Keras as a deep learning framework, we are not using pre-built transformer layer, right? That's a very important thing. So we are using here TensorFlow Keras as a deep learning framework. We are not going to use the pre-built transformer layer, right? So we will construct the important transformer component, ourselves, right? So first thing is the what is a transformer, why we are going to use it, right? So before writing a code, let's understand what is a transformer actually does. Suppose our sentence is like, the movie was absolutely fantastic. So traditional sequential models such as RNN process word one after another, right? But transformer introduce completely different idea. So instead of processing the sequence strictly one at a time, the transformer just examine the relationship between the different token using the self attention, right? For example, the movie was not good, so here not is extremely important to interrupting the good, right? So self attention allows the model to learn the relation between the different position in the sequence. So this is the one of the major reason transformer becomes so powerful in for the NLP, right? So if you see the original architecture of transformer, right? So the original transformer architecture introduced in the famous, the journals, we can call the research paper, attention is all you need, right? In this paper we the author introduced the transformer architecture, right? So if you see the architecture here, so it will contain, first thing we don't so basically however our task is to for the test classification, so we do not need decoder. So therefore our project is based on the transformer encoder, right? Because we are going to only work with the test classification, right? So if you see here the if you see the architecture of transformer, right? So you can see I'm going to write here in the transformer architecture on the screen. So first let me run this code, then I will going to write here in the form of text. So this is the architecture, this is the, let me write here the architecture, sorry. So if you see here the architecture, so this is the very important thing, this whole architecture is given in the attention is all you need research paper, right? So you can see this is the architecture here, you can see on the screen. So the transformer contain, this encoder, decoder, and every encoder contain, this encoder contains self attention, feed forward and output, right? So in this, for the text, we are going to use the text classification, so we'll use this first encoder, self attention, feed forward and output, right? So, and also there is a decode, in the decoder part there is a mask attention, cross attention and feed forward, but we will not use this, we will try to use this encoder only in our project, right? So you can see here, this is our complete architecture about the transformer, right? So we'll use the transformer encoder, right? So now after this loading the imported data set, now imported library, we just import all the necessary library. Now we have to load the IMDb dataset, right? So the same way, we have to first we have to use the vocabulary size, then we have to write the max length token. So I'm going to write here all the things here. You can see I'm going to write this part. So what is the meaning, why we are going to write here? So it's a very similar to the previous one. We are defining the vocabulary size is 10,000. That means we will work only with the 10,000 most frequent used word in the IMDb dataset. Then we will define the max length as a 200. So this means that every review is eventually be converted into the sequence containing the exactly 200 tokens. So IMDb dataset provide the Keras already by integer encoded. For example, we can see the, like a matrix kind of thing, by like a conceptual way, right? So each integer represent as a token. This point is that transformer doesn't directly understand the English word, so neural network operates a numerical representation. So you can see here, you can see the complete, like pipeline here, you can say the pipeline of this transformer. So in this our project, so you can see here that will be first, we will use the text, then we use the token, right? Then we use, so this will be the pipeline I'm going to write here, that will be easy to understand here. So first thing, we have to take the text, token, integer, embedding, and then we have to perform this transformer, right? So we have imported these things, right? So now we are going to move with the padding, right? Because we have a different review, different length. Different movie review has a different length. For example, review A is 80 tokens, review B is 150 tokens, or like review C is 300 tokens. So neural network generally work efficiently with the batch of the equal shape tensor, right? So now we are going to use the pad sequence, right? We have to define the token size, right? So for the pad sequence, we have to write a code here. So first let me execute this code here, because we have defined these things. So max length we have defined. So you can see here we getting these things. Yeah, so first we get the training sample is 25,000, test sample is 25,000, and we got the review also. Now we are going to use this padding, right? So for the padding, like we have to maintain, because we have a different review length, right? Different review has a different length. So we have to we have to perform the pad, or we have to perform the truncate, right? So for the truncate things, we are going to use this pad sequence, right? So for we are getting here, if we are going to write this code, you can see I'm going to define here extend t, so what is the meaning here? We are performing the padding post. It means the zero are added at the end of the sequence, right? We can see here we are performing this thing. This part is clear, right? We are taking the max length, we are defining this thing. So you can see here, going to use here the padding post, right? That's a very important here. So this, for example, like padding post means that the zero are added at the end of the sequence. For example, so suppose we are putting the 250 length here of the token size, we are putting 250, right? So it's if suppose the 180 is there, so rest part will be filled by the zero. So the zero represent the padding here. If a reviewer has a longer than 200 tokens, then we put the truncate, right? So therefore every review now exactly 200 position. If they are less than 200, so we will put the zero. If greater than 200 tokens, then we perform the truncate, right? So now we are going to understand the embedding. So a token ID such as 25, so doesn't contain the semantic information about itself. So we perform the transform into the token ID vector, right? So we have to perform this, we have to write the embedding dimension. Also we have to maintain the number head, we have to perform the other dimension, then we have to introduce the transformer block, right? how much the transformer block is required here. So I'm going to write here, this thing, so that you can understand easily. So I'm going to write here the embed dimension is 64, right? So let me run these things, because we perform this padding part. So you can, after the padding, you can see we got the training size is 25,000 by 200, right? So all these things we got here. Now we are going to write here, right? So you can see why we are writing here the embed dimension 64. It means each token will represented by 64 dimension vector, and number head 4, it means the multi head attention will contain the 4 attention head. FF dimension, it means we are putting 128 here, represent the hidden dimension of the feed forward network. And the number transformer block 2 means we will stack 2 transformer enable encoder blocks, right? And finally we drop out, help reduce the overfitting. So we are putting here the dropout rate is equal to 0.1. So finally we drop, with help of this dropout, it will reduce the overfitting, right? After that we have to perform the positional embedding. So self attention doesn't inherit whether the token is appear first or second or third. Consider dog bites man or man bites dog. The same words are present, but their ordering change the meaning. So therefore we need positional information. So now we have to define one function, that the token positional embedding. So now we are going to perform here the positional embedding. That's the most important thing here. So now we are going to write here, we are going to perform the positional embedding, right? So let me write here, we are performing the positional embedding here. So for this we have to define here the one functions. We are going to def init self vocabulary size, maximum let, and embedding dimension. So we have to define the constructor that receive the 3 important values, right? So let me write here the code. How can we write these things? Because first thing I am going to define one class. Inside the class we are going to perform the constructor, right? Then we have to define the self attention token embedding. After the self positional embedding we have to define this. So first let me write here, then I will try to explain. So from you can see here from the top, first we define the class here, right? Inside the class we have defined the constructor. So this constructor receive the 3 important values: self, vocabulary, max length, and embedding, right? So you can see here we have getting the 3 value in this constructor we are getting, because we are going to try to become the constructor here. So this, after this we writing the self token embedding layer, right? So this is the this part you check here. So what is the meaning here? So this create a trainable embedding matrix, right? Suppose we have 10,000 tokens, 64 dimension, so it's become 10,000 by 64 matrix. So this model learn this matrix during the training, right? After that we are going to write here the self position embedding, right? You can see here we are writing here self position embedding. So what's the meaning of here? So position 0 is a vector, position 1 is a vector. So this create a vector representing position, right? After that we are going to write here the sequence length, T shape, right? So that's get the sequence length dynamically, right? After that we are writing here this position TF start 0, and we are writing here this part, right? So what's the meaning here of these things? So we are creates like a 0 1 2 3 9 9, okay? So we are creating a one vector length, right? After that after that we are going to return this embedding, positional embedding. So you can see here is we just combine the semantic information and positional information. So if you see by this code you got the output like this. What is, if you see here, if in the form of text, what you are doing in the above code? So basically we are performing this thing. First we try to perform the token embedding. You can see we are writing the token embedding, then we are going to perform here the positional embedding, and this is the conditional embedding, and finally the transformer input, right? Now we are giving this transformer input here. So this thing we are performing in this above code, right? So let me run this code here, this token and positioning part. So I'm going to run this here, right? So now you can see here we are getting this code is working fine, right? So basically this thing we are going to perform here. After that we have to perform the self attention, right? So this is the heart of the tutorial, right? This is the heart of the video. Self attention use the 3 representation: query, key, and value, right? So if you seek the basic formula, that is attention QV. I'm not able to write here the basic formula, but I'm try to explain you the what is the self attention here. So self attention is basically use this query key and value, right? So query represent the what the tokens is looking for, right? Keys represent the key represent the what information token contain for matching, and value just contain the information what exactly be aggregated, right? So this is the self attention part, right? And that will produce the then the we have to create the matrix q k transpose. So this and after that we have to divide the matrix. So finally that will produce the similarities scores, and now we have to stabilize the values. Then we have to perform the softmax that will convert the score into the attention weight, and finally we get the attention weight into V, right? So this produce the conceptual representation. So now we are going to build a multi-headed the self attention, right? So that is the most important thing. We are going to build the self-headed attention, right? So now we are going to write here this, we are going to build this self attention here. So let me write here, I'm going to write this thing here. So first thing we have to perform, right? So first thing we have to define the one class here, right? We have to define one class. So after that we have to check the dimension. So we have to assert the dimension and we have to divide with the number of head, because we need to divide the embedding dimension among the attention head, right? So I'm going to write here the complete things. You can see first we are taking here. Now you can see this part, right? First we initiate the constructor, right? Then we are talking about this part, right? This is a very important thing here, because we are performing this thing. So first thing we are going to, because we need to divide the embedding dimension among the attention head. So we have embedding dimension is 64. So then we number of head will be the 4, right? Because 64 by 4 is 16. Embedding dimension is 64, number of head is 4, so therefore 64 by 4 is 16. So each attention head get the 16 dimension, right? And after that we are going to define the query key and value. You can see here we are writing here the query key and value, this thing, right? Because this is the concept of self attention. So these are the transformations. This input this input representation and is the transform into the q, k and v, right? So each transformation learn the different information. Now we are going to split into the head, right? So you can see here we are writing here the batch size -1 here. You can see this part, right? This is important, this is also very important, So here suppose what is the logic behind it? Suppose batch size is 62, sequence is 200, embedding is 64, head is 4 and head dimension is 16, right? So before splitting it will be 32 by 200 by 64. After receiving it's become the 32 204 into 16, right? Because this 64 is the head and the head dimension 4 into 16, right? Because we have already divided by 64 divided by 4 becomes 16, right? After that we will perform this transpose, right? So you can see here this part. After that we going to this perform this transpose, right? Now we are coming to this part, right? Why we are writing here? So here this is the attention score, right? We are going to convert this into the attention score here. So this perform the resulting shape in the particular in the particular batch head sequence, sequence size, So this is an important thing. You can see this is the batch size, key and batch size. This is a key, query key and value, right? So we are again defining here query key value. After that we have to perform the attention score, that is we call the scaling, right? This is after that we are going to perform here these things. So without a scaling, dot product can become very large when the when the dimension is increased, and large value can make the softmax extremely picked and produce unstable gradient, right? So dividing by the square root of the head dimension help to keep the attention very fast, right? After that we are going to perform the softmax here, right? You can see we are writing here the softmax, going to perform here the softmax, right? Where is the softmax? This part, right? So we are going to perform this softmax. Why we are writing the softmax here? Because softmax convert the score into the different probabilities. For example, token A is a 0.5, token B is 0.1, and the value, if you check the complete addition, the value become approx 1. So this tells us how much attention should be given to the different tokens, right? After that we have to perform this weighted value, right? So this perform the actual attention operation, right? Weighted value, weighted output, right? We are putting here, and now you can see, now we are going to perform the transformer encoder, right? So after the weighted value, now we are going to perform the transformer encoder block, right? So you can see here what we perform here, now what we are going to perform after these things. After this, you can see we have to perform this multi-headed attention, residual connection, layer normalization, feed forward, and residual connection, and layer normalization, right? So after that, we are going to write here. Now we are going to understand those things, the transformer encoder block, right? That is the most important. So first thing we have to write here, in the transformer encoder block I am going to perform here, right? So let me write those things for the transformer encoder. So I'm writing here, let me check with let me write here in the form of text. This is performing the code for the transformer encoder, right? So here I'm going to write here this transformer encoder, right? So you can see here what we are performing these things, right? So first thing is that we are going with the we're taking the input sequence into goes through the self attention, right? So you can see we are writing here the we are writing the same thing, we are writing self return. Let me check once I am getting something. Yeah, let me write again the we are going to write transformer encoder, right? So first thing, the important here, we have to define here the uh, yeah, we have to define the self embedding dimension and number head, right? So I'm going to write here, we are going to define those things. Okay, yeah, it's working fine. So let me write here these things. We are going to define this transformer encoder block here, right? Then we are performing, first thing we are going to perform here, so attention output, right? That is a self attention required, and after that we are going to write the attention output and self drop route. So this random disable the sum activation during the training, right? This we are talking about this attention output, right? Where is the attention output here? I'm talking about this part, right? So you can see here, so dropout, this dropout rate randomly disable the sum activation function during the training. It's also help to reduce the overfitting, right? Now we are doing the residual connection, right? So you can see the output one, this part, this is performing the residual connection, right? So this is the we are adding here the original input plus attention output. So this is called residual connection, or we can call the skip connection. Why it is very useful, residual connection? So deep neural network can become difficult to optimize as they get deeper. So residual connection provide a direct pathway for information and the gradient. So now we are going to talking about the feed forward network, right? So you can see here we are writing here the self FNN. So that is the feed forward network we are writing here. This is a feed for FNN represent the feed forward network, neural network, right? So here our dimension become the 64, 128, 64. The first dense layer expand the representation. The second dense layer project into the back to original embedding dimension, right? So now we are also using the second residual connection, input and feed forward. Okay, so we finally got the, this is the second feed this is the second feed forward. If you see, this is the first one, this is the second one, right? This is the second one. After that, now we are going to build the complete transformer model, right? Because we have to perform the transformer classifier, right? So now we are going to combine everything inside the building, the inside building this complete transformer model, right? We have to combine all those things, right? So let me write here, how can we combine all those things? So we have to we have to define the transformer classifier, because now here we are going to perform the transformer classifier, right? After that we have to let me write here, then I will explain what's the meaning here. So I'm going to see first, let's start with the, we are going with the define the transformer classifier, right? After that you can see here, we are going to perform x equal to self embedding, right? That is the input. We can see from here, we are going to define as a x embedding, right? So I'm talking about this part here, right? This part we have already taken, now we are here, we can see x self embedding, right? So it means the input will be the batch side and batch size and 200. So that's become the batch size 264. Now the sequence has a 64 dimensional representation for every position, right? After that we are going to perform the this self transformer block, right? You can see here we are writing here the self transformer block, right? So what's the meaning here? So the allow us to stack the multiple transformer block. So you can see here this number of transformer block is 2. It means the embedding transformer block 1 and transformer block 2. After that we are also using the global, global average pooling, right? So that is basically after the transformer we are going to use here, so it means the global average pooling convert into the batch into 64. So basically it summarize the information, access the sequence, right? Then we are going to use the self classifier here, right? So it will convert into the, self classifier. You can see here it's convert into the 0 1 1, right? This is the self classifier that will convert into the 0 1 1, because we are, that's a binary classification. So after that, once we complete this transformer block, so then after we have to create a model, right? So in this model we will call the transformer block. We have defined one function, name of transformer block. So inside model we will call all those, so let me call the transformer block. Then we have to define the vocabulary, we have to define the vocab size, max length, number of headed, embedded dimension, everything we have to define here, right? So let me write those things here. So let me we have to define here all these things. So first we have to start with this model transformer. After the embedding, see the, if you see the expected output, so output will be in the form of 2 in 1, when we will perform this, create this model. So let me write here, right? So we are going to create this model here, right? So you can see this is a output shape is a 2:1, right? So we created a two dummy example, just add make to share our model can process the expected input in shape of in the input shape will be 2 into 200. So it means to review is containing two tokens, and the output size will be 2 into 1, because this review the receive the sentiment probability, right? After that, now we are going to use this, because we have to just perform the, we have to check the model architecture. So now we are going to call the model summary, so that we can check the complete model architecture, right? So that we can understand our model, how the model is working, right? So finally you can see here, this is the model architecture here, right? So this is a token positioning, transformer encoder 2, because we are using this two encoder block, right? Then we are using the global positioning dropout range 4, right? So you can see here we are able to understand all the things here, right? So you can see here model summary allow us to inspect the architecture parameter count. Notice our, we can notice that the, these are the trainable parameter inside this model: token embedding, positional embedding, query projection, key projection, value projection, output projection, feed forward layer, normalization layer, and classifier. Now we are going to just compile the model, right? Because we have to use, again we have to use this binary cross entropy and the Adam optimizer, right? So now we are going to use here the going to just execute the model here. So now we are going to compile the model, right? So you can see here we compile the model here, fine, it's working fine, right? So we have used this Adam optimizer, learning at is 0.01. It's 0 represent for negative, 1 for positive, and this is a binary classification model, right? Now we have to train our model, right? So for the training the train the transformer, we have to write this model dot fit, and we have to, again we have to put the number of epoch, right? So now we are going to write the number of epoch is 5, right? So you can see here we are writing the number of epoch is 5. So because it's still we are using this CPU, so it will take more time. So again we have to go to the runtime. You can say it's taking 6 minutes, 7 minutes, it will take long time. So now we are going to change the runtime here, and we are going to select the this T4 GPU, and now we are going to run the all the block here, right? We click on the run all block. So you can see it will take some time, but it will be fast. So inside this model train we are using this train for 5 epoch, and each epoch means the model has processed the complete training data set once, as the batch size will be 64, that the model processes 64 example before updating the weight. So we reserve the 10% of training data for the validation, right? So now after these things we have to check the training curve also. So first we try to complete the this training part, because we are now using the GPU, so it will take some time, because we have to again restart the we have to stop the CPU, and we have to shift into the GPU things. So I think it will taking some time. So you can see fine, now you can see it's a fine, yeah, it's a totally it's very fast. So you can see here now that we are coming to epoch 1 here. So you can see the speed here, right? So within a second, you know previously when I using the CPU, so it will taking 6 minutes, now you can see here within the second, this epoch 1 is completed within the 3 second, right? So you can see the how can we use the GPU to just increase our just reduce our computational time, right? So that's the beauty of this GPU, right? So you can see this speed of GPU, right? So accuracy is 95%. That's great. Yeah. In the epoch 5 we got the 95% accuracy. So you can see here, let me plot this graph here to check the training accuracy and all. So you can see here we are getting the graph accuracy like this, right? So after that we have to check for the loss here. Loss curve we are going to check here. So simple thing, in the previous code of we are going to change here, in place of accuracy we are going to write here the loss, right? So that will be the same. So I'm doing the copy paste of the previous code here. In place of accuracy we are going to simply going to write the loss, right? So you can see here in the place of in place of accuracy I'm simply writing the loss here, right? So you can see we are getting these things. So this is a fine here. Now the important thing, we have to just we also check the test evaluations, right? What is the how they evaluate model using the test data, because we have built our transformer model and training data. So now we are going to check on the test data evaluation, right? So we are going to perform here on the test data, right? So we can sign this code is not saved, so we have to click here on the save, right? So it's the saving, right? We have to remove this point. You can see we are getting error here, right? So it's not save. We are going to save here. Let me save those things. Okay, fine. Now it's saved, right? You can say save successfully. That's a fine. So you can see here we are getting the test accuracy here. Because we have to finally evaluate our model using the test data set, and the test set was the not used directly update the model weight during the training. So therefore test accuracy give the estimate how the our transformer on the unseen review, right? So that is the fine. So if you check the architecture recap here, so let me come to this architecture part here, what we perform here till now. So we are getting accuracy is very fine, if we are getting 95% accuracy, and you can see here we the test accuracy is 83%, right? Test loss is 0.47. Now we are coming to what we try to recap those things. So you can see this is the complete architecture we perform here. First we take the review, convert into the integer token, then we perform the token and positioning, right? Okay, so let's why we using this transformer. So let's summarize it. So let's answer very important question, why did transformer become so important? So one measure is the ability to model relation between the tokens using the attention. So RNN process only the sequence sequentially, right? But transformer can process the representation of sequence much more efficient in the parallel during the training. Another important thing, advantage is the self attention can directly connect the tokens, and that that are the far apart in the sequence, and this made the transformer architecture extremely useful for language understanding, even in the architecture such as BERT, GPT, and many large language model, right? So you can see here we perform this thing in our in project. We input integer tokens, then we token image positioning embedding, then the transformer block we use the multi-headed attention, add the layers, feed forward, then add the layers. We use the two transformer block here, right? Then we use the global average positioning, and then sigmoid and positive negative, finally the classification thing, right? So we perform these complete things in our project, right? So now we are moving to here. This is a complete architecture here. So now we are moving to important thing. What is the difference between the RNN and transformer? So for the sequential processing, RNN is fine, not strict the recurrence, right? In the transformer, that is not strict to recurrence. Self attention in RNN, no, we don't have a self attention in RNN, but in transformer there is self attention. Parallel training in transformer very strong, but in RNN it's very limited. Long range relationship in RNN most difficult, but in transformer very easier. So main mechanism is in the, if you check the both main mechanism in RNN and transformer. So in the transformer use attention, but in the RNN we use the hidden state, right? So you can see the transformer is the backbone of modern LLM foundation, right? So this is the very important thing here. This is now now we are talking about the important things. Why we multiple heads, right? So this see suppose we are taking with one example. The movie was not good, not very good, because the story is predictable, right? So different attention head can potentially specialize in a different relationship. First head will be grammatical relationship, second head is a semantic relationship, third is the conceptual relationship, fourth is a token relationship. So multi-head attention allow the modern to perform the several attention operation in a parallel. Instead of having a single attention mechanism try to capture the every type of relationship, multiple headed can learn in a different pattern. So after the calculating the attention independent way, the head can combine back into the original embedding, right? So that is the important thing here. So what is the feed forward network? So see, self attention allow token to just communicate with each other, but feed forward network then applies non-linear transformation to resulting the representation, right? So you can think the attention is a mechanism for contextual information exchange, while the feed forward network process the information in the information of each position, right? So that's a very important thing, right? We have learned here. So now we try to summarize our video what we learned here, right? So first thing, so we have successfully built a transformer encoder from the scratch using the Python and TensorFlow. So let's quickly recap with the implemented, right? What we implemented. First we loaded the IMDb data sentiment data set, then we converted all the sequence into the fixed length using the padding. After that we created a token embedding and positional embedding. Then we implemented the multi-head self-attention manually. Inside the attention we generated the query key value representation. We calculated the Q key transpose, and then we just implemented a transporter encoder block that containing the multi-headed self-attention, residual connection layer, normalization, feed forward network, residual connection layer, normalization. So finally we stack the transformer block, added a classifier headed with the sigmoid activation. So our model then learned the classifier, movie review, and positive or negative. So important takeaway is the transformer is not just a magic, it's a core of that carefully designed the combination for embedding, positional information, attention, feed forward network, residual connection, and normalization. So once we understand this component architecture such as BERT, GPT, and many modern language, so it's become easier to understand. So if you found this tutorial useful, make sure subscribe the ThinkLab by Saurabh. In the next tutorial we can go into deeper like BERT, GPT, and attention visualization and building the mini language from the scratch. So thank you for watching. I will see you in the next video. So happy learning.